Hello, chemistry students. This is Professor Sean McMahon with Lecture 3 for Chapter 8, Gas Laws. And in this particular lecture, we're going to just finish with a quick review of gas stoichiometry, and we're going to introduce the last law that you really can't rearrange using the ideal gas law, but it's a pretty simple law, especially for purposes of this course. So, without further ado, let's do a quick review of gases and stoichiometry. And the reason why I want to do this is, again, stoichiometry is kind of the centerpiece of this course. What I mean by stoichiometry is in reactions, if you're given a certain quantity, you can determine how much of another quantity is produced. We did this earlier with gravimetric, where we were converting grams and molecules using balanced equations. And now with gas laws, we, in last lecture, introduced the concept of combining volumes and doing volume stoichiometry, and then using molar volume at STP. We use that in 1 mole of any gas, there's 22.4 liters. And that's a very powerful thing because it creates a conversion factor that allows us to continue doing stoichiometry. There are gas law stoichiometries in non-STP conditions, and we can still solve those using our mole-to-mole relationships. And what we can do is we can do that using the ideal gas law equation, maybe an Avogadro's law where it has a change in conditions. So we will cover that. For the most part, I don't try to do too much of that. I do focus on STP conditions for this course. It's a little more straightforward, a little bit easier, but I am still going to cover non-STP conditions and show you how you can apply everything you've learned in stoichiometry up to this point and the ideal gas law for those particular problems. So let's review. So we did this last time, and this was what volume of O2 is needed to react with 15 grams of aluminum at STP. So again, I'm given a quantity of a substance, and I want to know a different quantity of a different substance, and I know there's a reaction. They give me the balance equation. They don't have to. They could have said it was a combination reaction with aluminum and oxygen, and then you would have written out the aluminum oxide and then balance the equation. Now, what you can do is know that this is going to require stoichiometry because we're also converting to liters of another substance, and we know that this substance is going to be a gas. They state it, and it's under standard temperature and pressure conditions. So we can say 1 mole of any gas is 22.4 liters at STP, and that's what they want. They want liters. So what are we going to do? We're going to convert, just like we did before, the 15 grams of aluminum to moles. And how are we going to do that? Molar mass. It's actually 26.98 grams of aluminum per 1 mole. So that's what I got to do. And then moles of aluminum, I can convert to moles of O2 because there's 4 moles per 3 moles of oxygen. So 4 moles of aluminum to 3 moles of oxygen. And then 1 mole of oxygen at STP is 22.4 liters. So we get the 9.33 liters. So that's where, again, we're using molar volume at STP to create a conversion factor that allows us to do stoichiometry. Pretty straightforward. Can it be a little more challenging? Of course, we could have a problem that's not under STP conditions, okay, and still request, okay, it could still request volume. So I picked another one. How many liters of oxygen? So again, I'm trying to do liters of oxygen. Is formed with 294 grams of potassium chlorate in the following reaction. So I'm given grams of potassium chlorate. I can convert this to moles of potassium chlorate using molar mass, and then I can convert it to moles of oxygen using our mole-to-mole ratio. If this was at STP, I could say 1 mole of oxygen is 22.4 liters, but this is not at STP. The pressure is 755 millimeters of mercury, and the temperature is 305. Standard temperature is 273 Kelvin. And standard pressure is 1 atm, where 755 millimeters of mercury is just shy. So we cannot use the molar volume of 1 mole is 22.4 liters. However, we can still use our stoich, as we did in the past, and determine moles of oxygen. And once I figure out the moles of oxygen, I know the pressure and I know the temperature, and I can solve for a volume of oxygen using PV equals nRT. So I'm going to use the stoichiometry to get moles, and then the given pressure and temperature to get volume. So PV equals nRT, I just put the O2 because that's the gas. And we see, what type of reaction is this, by the way? I start with potassium chlorate, and I end with two products, potassium chloride and oxygen. So this is a decomposition. I have one substance breaking down to multiple. So I'm clearly stating the O2 because that's the gas. And this is asking liters of oxygen gas. So I'm first going to use my stoich and convert. I have a balanced equation, convert the given units to moles, convert the given moles to the moles I want. I want oxygen. Obviously, I want liters, but I'm first going to at least get moles. And I can't go directly to 22.4 liters because it's not at STP. So I convert the 294 grams of potassium chlorate using the molar mass. There's 122.55 grams potassium chlorate per 1 mole. So now I'm at this step. 1 mole of potassium chlorate, if I want to cancel that out, I go, well, there's 2 moles of potassium chlorate per 3 moles of oxygen gas produced. So now I can cancel this 1 mole, the unit, 1 mole. So now I have moles of O2. So this gives me moles of O2. So now I can utilize PV equals nRT, divide both sides by P, because I'm looking for volume. We found the moles, right? Here's my N. And now I can convert my pressure, which is 755 millimeters of mercury. I can say when 1 atm, there's 760. I can get my atm. I should have 3 sig figs, so I underline the 3, but I want to reduce round-off error, so I just leave that. So now I have my pressure. And the temperature, the nice thing is they did give me that to Kelvin, so now I have my temperature. So now I plug everything into my rearranged formula. I have my 3.60 moles. I have my R, which is a constant, and I want to make sure the units of moles cancel. They gave me Kelvin. I changed it to atmosphere so that atmospheres can cancel. And now I'm going to be left with liters. And the final answer is 90.7 liters. Okay. Now, again, if this was at STP, it'd be a lot easier, right? Because at STP, you would just have one more conversion factor. 1 mole of any gas is 22.4 liters. And you'll see it's very close to this, but it will be slightly different, okay? And actually, you know, might as well do that. Might as well give you that number since I'm here. So 3.6. Oh, well, it's more than slightly different. Yep, it comes out to 80.6 liters. So we can see that, you know, under standard temperature and pressure, there's a difference. That's why you would have to use that, okay? So that was kind of a review of the stoich, was kind of a review of our ideal gas law. But now, one of the things that we really didn't talk too much about, but most of the gases that we're interacting with are mixtures, right? So air is a mixture. And according to kinetic molecular theory, each mixture of gas, because the gases are not really interacting, right? Because when they bounce off each other, they don't stick, they behave independently, they're elastic collisions. What we're going to notice is each individual gas exerts its own pressure, which essentially is it's a type of partial pressure, right? So the sum of the parts equal the total. So there's a law, it's pretty straightforward. It's basically Dalton's law of partial pressure, and is for all the pressures of the gases in the mixture, you add them all up, whether there's 3 or 10, you're going to sum them all up to get the total pressure. So here's an example of partial pressure for air, right? So nitrogen, which is roughly 78.2% of air, its partial pressure is about 594. Oxygen, which is about 21%, is about 160 millimeters of mercury. Carbon dioxide, argon, water vapor, it's about 6 millimeters of mercury. And if we add this all up, we get 760 millimeters of mercury, which is roughly 1 atm. So we can see that all we're really doing is adding up the parts to get the total, right? So like this could be your nitrogen, this could be your oxygen, this could be like CO2, and then you'd have water vapor, you'd have argon, you keep going, you add it all up and you get your total. So could we do a partial pressure problem? Of course. An atmospheric sample containing nitrogen, oxygen, and carbon dioxide, if the partial pressure of nitrogen is 587 millimeters of mercury, oxygen's 158, and carbon dioxide is 7, what is the barometric pressure in millimeters of mercury? So nitrogen plus oxygen plus CO2, we add those all up. We're going to the 1 unit for all of these, and then when we add it all up, we get 752 millimeters of mercury. Now, could we change this to atmospheres? Sure, you could easily change that to atmosphere. There's 760 millimeters of mercury for 1 atm, and you could do it that way if it asked. Didn't really ask that. It just said, what is the barometric pressure in millimeters of mercury? So you're done. So here's one that's a little bit different. A scuba tank contains oxygen with a pressure of 0.450 atm and helium at 855 millimeters of mercury. What is the total pressure of mercury in the tank? So, I guess I didn't, my bad. I thought this is the one slide where I didn't do it for you guys. It's okay. We know that the total pressure, okay? The total pressure is what? The pressure of oxygen. I think the oxygen is, right here, plus the pressure of helium. The total pressure, right, is that 0.450 atm plus the 855 millimeters of mercury for the helium. Now we see that we didn't have to do anything. They asked for the total pressure in millimeters of mercury. So what we need to do is we need to change the atmospheres to millimeters of mercury. Well, how? 1 atm is 760 millimeters of mercury. And I bet when you do this, it equals 342, because we basically have half an atmosphere and 342, right? So, it's pretty close to half. The 380 would be half an atmosphere. So it's 342. We add, we're going to the ones place. So when we add this up, we actually end up, instead of just 3 sig figs, 4, because we're not using the number of sig figs like in multiplication and division. We're using precision, which is the ones place where you could have more or less after you do addition and subtraction. And in this case, we have more, 4 sig figs. Now, if they had asked for you to convert this to atmospheres, you could. You could convert this to PSI. You can convert this. I would give those to you, right? So like if there's 14.7 PSI in 1 ATM. So like if you wanted to convert this to PSI, you could say, well, there's 760 millimeters of mercury per 14.7 PSI, because they're both equal to an atmosphere. Or you could go the long route, 1 ATM, and then 1 ATM, 14.7 PSI. So that would give you your, total pressure in PSI, okay? And you could have done that in the prior step too. All right, so that is basically Dalton's law of partial pressure. Now, a lot of times what you'll be seeing is that you'll be performing actual aqueous reactions where gas bubbles out of a solution and you collect the gas, okay? And we had talked about earlier how vapor pressure, above any liquid, there's vapor pressure because some of the liquid's escaping to the gas phase, exerting a pressure. So if I'm collecting gas over water, the total pressure will not only be the sum of the gas being produced in the reaction, it'll also be the sum of the water. So with Dalton's law of partial pressure, it's useful in aqueous reactions where you're producing gas, where we can figure out the total pressure through the barometer, and then we could figure out the pressure of the water based on temperature, because there's tables with water's vapor pressure at different temperatures, and we can then just get the pressure of the gas. So what's an example? Well, there's tabulated vapor pressures. So here's an example of water vapor pressure at different temperatures. And what we notice is as the temperature increases, right, we know, according to kinetic molecular theory, as temperature increases, things move faster. So if the liquid water is moving faster, if it's moving fast enough and it's at the surface, it's going to escape and produce a gas, a vapor. So you can think of it as an escape velocity overcoming the intermolecular forces that keep the liquid particles sticking into a condensed phase like a liquid. So if I have a really fast moving liquid particle, it gets to the surface, it can escape and overcome the intermolecular forces. And that exerts a vapor pressure above the liquid. Well, as temperature increases, so does vapor pressure. And we know, we can see it directly here, and it's actually exponential. And what we'll notice at 100 degrees Celsius, you'll see a vapor pressure of 760 millimeters of mercury, because that's the normal boiling point. So at 100 degrees Celsius, the water can escape anywhere in the liquid because it has enough kinetic energy to do that. That's why that's referred to as boiling. It doesn't have to just be at the surface. But the main part of this is to understand that at any given temperature, water is going to vaporize and provide a partial pressure. So what does that mean? Well, let's say I have a reaction where I have zinc as a solid and hydrochloric acid. Now, everyone in here, we should be able to look at this and recognize this is a single displacement reaction. I have an element in the metal, and I have a compound. So the zinc is going to displace the hydrogen because it wants to lose electrons, and right now the hydrogen has a positive charge, and if zinc loses the electrons, it can accept it. So it will kick the hydrogen out as a gas, because hydrogen in elemental form is in the gaseous state. It's a diatomic, and I will produce zinc chloride aqueous. Well, that's not really a production. Basically, the zinc will dissolve. Well, and I need to balance this. If I have this reaction occurring, I can actually feed the hydrogen gas and collect it. So I can take, let's say, a bottle, fill it with water, invert it into a pool of water like a trough, and then I can collect the zinc, or sorry, not the zinc, the hydrogen gas in this bottle, and it will displace the water and push the water out as I'm collecting the hydrogen gas. As it's doing that, what we have to realize is, so here's my hydrogen gas, right? So these diatomics, these are two little hydrogens. What I also notice is that the water is also vaporizing. So the total pressure inside this container, because again, what is pressure? Pressure is directly proportional to the number of collisions. Okay? Some of those collisions are going to be from H2, but some of them are also going to be from the H2O. So the total pressure, the total collisions are the collisions from the gas, the hydrogen that I'm producing in this balance equation, and the water that normally vaporizes. And the reason why this is occurring where I'm getting water is because I'm collecting it over water. So what I can do is, there's actually a lab at Miramar where we do this, which is, I love this lab, by the way. It's probably one of my favorites, is we actually use odometers. An odometer is basically an open-ended tube. We use an odometer to collect the gas. And what we'll do is we know that atmospheric pressure is going to be exerting a force. So there's in the atmosphere gases, and they're exerting a force on this liquid, which is water, let's say. And then there's gases inside the odometer. If we level out the liquid in the odometer with the liquid in the pool, basically the container having the odometer, what we'll say is that the total pressure inside the odometer, because it's at an equal height with the outside water level, is atmospheric pressure. And then the pressure of the gas, well, I just produced from the single displacement, is the hydrogen gas. And the pressure, whoops, I'm getting really sloppy here, sorry. Of the water vapor. So I can take the barometric pressure. Let's say I look at the barometer and it tells me it's 755 millimeters of mercury. Then I know that this total pressure is also 755 because the atmospheric pressure is the same as the total pressure inside here because we have them at equal levels. So now to get the pressure of the hydrogen gas, I need just the pressure of the water vapor. And I can do that because I can record the temperature of this water, right? I can record the temperature, let's say in degrees Celsius, and say that the gas in here is roughly the same temperature of this water vapor, right? And then I can use a table. Let's say that the pressure is 20 degrees Celsius. So I record the temperature of the water. It's 20 degrees Celsius. So I'm going to assume that this water vapor is also 20 degrees Celsius. So now I can substitute the pressure of the water vapor that's being collected simultaneously with the gas I produce is 17.5 millimeters of mercury. And now I can just subtract 17.5 from both sides to get the pressure of the hydrogen. So that's kind of the power of Dalton's law of partial pressure. The sum of the parts equals the total. And you could apply this with aqueous reactions where you're collecting a gas, like in single displacement, over water. So that's essentially Chapter 8, gas laws, for this particular chapter, for this course. And thanks so much for tuning in. I appreciate it. And we will continue by moving on to Chapter 9. Thanks so much.